Hello everyone, my name is Manish Gupta, and in this video I will talk about how to handle defective suggestions and prefixes in query auto-completion systems. Specifically, the agenda is as follows. First, I will talk about LSTMs for inappropriate query suggestion detection. Then I will talk about offline spell correction. And lastly, I will talk about online spell correction for prefixes for partial typed queries in autosuggest systems. So let's get started. Let's talk about the LSTM kind of method for inappropriate query suggestion detection. As you see in the examples below, inappropriate queries are any kind of suggestions that may cause anger, annoyance to certain users, or exhibits lack of respect, rudeness, discourteousness towards certain individuals or communities, or may be capable of inflicting harm to oneself or others. Right? They are toxic suggestions. They are hate speech content. And in general, it's a good idea to avoid showing such suggestions in the drop-down in the autocomplete systems. Uh, One of the first systems which tried to act in this direction proposed a convolution plus BiLSTM kind of a method called as convolutional BiLSTM kind of method for inappropriate query suggestion detection. So the idea is given a particular query suggestion, the output, the expected output is a binary classification of whether the suggestion is appropriate or not. The query is essentially expressed in terms of word embedding. So each of those words are embedded. In this particular case, they used something called as DSSM word embeddings. However, one could use any other word embedding method. Further, this particular embedding matrix, so if the query had 24 tokens, you would basically get a 24 cross 300 matrix. This matrix is then acted upon by several layers of convolution and of course the ReLU activation, followed by some pooling, which is then followed by two layers or rather by a layer of bidirectional LSTM. Um, Here, the word embeddings were randomly initialized, but as I mentioned, one could use any other word embedding method as well. Also here, three different convolution layers were used, but you could again use different number of convolution layers. So in this time period, convolution plus LSTM kind of methods were pretty popular for various kinds of NLP tasks. And that is why convolutional by LSTMs were proposed for this classification task of predicting whether a query suggestion is appropriate or not. Uh, the data set, the work also made publicly available a data set of such inappropriate queries, which consisted of several kinds of inappropriateness: extreme violence, self-harm, illegal activity, race, religion, gender inappropriateness, and so on. So several kinds of inappropriate kinds of queries. Um, the data is nicely divided into trained, validation, and test set. The first kind of model that comes to mind to remove such inappropriate suggestions is a pattern and keyword based filtering method, where you would try to come up with some blacklists and whitelists and then sort of do filtering based on them. Another kind of methods which are popular are to basically use engrams as features and uh, build traditional machine learning classifiers based on such engram frequency, like boosted decision trees or SVMs. Also, these methods can be combined with word embeddings like DSSM word embeddings so as to come up with good classifiers. Lastly, of course, several deep learning methods were compared, including the proposed convolutional BiLSTM method in this work. And they observed that across all the across these classes, they observed that they get a very good F1 score of about 87% with a precision of 92% in terms of predicting a suggestion as inappropriate or not. Okay? So that's the first method. And the idea is that if you can predict that some suggestions are inappropriate, you would delete them from your historical query logs and not include them as part of tries. Remember, tries based on historical queries are the most popular ways of coming up with suggestions in an autocomplete system. So if your tries do not have any inappropriate suggestions, the probability of you won't be, your methods would typically not surface them as part of your auto suggestions. Okay? So the first method. The other method that I'm going to talk about is offline spell correction. So the idea here is that while you have taken care of inappropriate suggestions and removed them from query logs, there are several times that users type in queries which are misspelled. So search engines have been coming up and designing various kinds of mechanisms of automatically correcting such queries. Now, such mechanisms are super important because they help you ensure that the spell corrected query becomes a part of your tries. In fact, what you could also do is to burn redirections from misspelled queries to spelled queries in your tries so that even if the user types in a misspelled thing, you can actually still show the spell corrected results as that results in the drop down of the query autosuggest system. So what is a popular way of doing spell corrections? Here is a popular way of doing so. The problem can be modeled as a sequence labeling problem. So the idea is you have n words in the input or n characters in the input, and you want to output n characters as well. More or less, the number of characters in the original query and the spell corrected query are more or less similar, except for a few little changes. Only a few characters need to be changed so as to do the spell correction. Right? For example, here is an spell incorrect Chinese query, and here is a correct Chinese query. Similarly, this is an incorrect Chinese query, is the corrected version. Okay? If you look at the translation, well, the translation differs a lot. In Chinese, of course, every character carries a lot of meaning. So one small little error can actually mean that Egypt has pyramids becomes Egypt has golden towers. Similarly, the correct thing was he has a strong desire to survive, and this one becomes a strong desire to win. Okay? So the idea is that we have to come up from a misspelled query, we want to get the correct query. Now, a nice way of doing so could be to use BERT to actually select a few characters that might have spell mistakes and then correct them. Okay. However, the way the BERT model has been pre-trained using the masked language modeling laws, that particular way of pre-training sort of means that this method of using BERT is suboptimal. BERT is really good at correcting things, but is really bad at detecting misspelled ones. So that is why these folks proposed something called a soft masked BERT. Now, soft masked BERT is an interesting model. It essentially works in two parts. The system has two main parts to it. The first part is error detection. The second part is error correction network. So the error detection is based on bidirectional GRUs, as we will see in detail on the next slide. But the error correction is surely going to be based on BERT. Okay? So the error detection network basically gives the output to error corrector, which in turn leads to the corrected query. So as you see here, this is the model architecture. Here is your original input. Let's say the original input has 4 characters. The detection network is going to come up with the probability GI that the ith character is incorrect. Now, depending on what is the incorrect probability, you are going to come up with the representation for every character, which is a linear combination of its original embedding and the embedding of the mask embedding, right? So with the correct probability, you essentially use the actual embedding. With the incorrect probability, you use the mask embedding. And that gives you soft masked embeddings, which go as input to a correction model, which finally leads to the corrected query. Okay? So here the detection network is going to be GRUs and the correction network is going to be BERT. Since there are two parts to the network, one the detection part and the correction part, therefore there are two loss functions. A detection based loss function, did you detect the character which was incorrect correctly, right? And then the second part is the correction loss, which is about once you have been pointed out that hey, this character was incorrect, were you able to correct it out nicely? Okay, so that's how these two networks sort of work together so as to come up with the final output, which hopefully matches the ground truth. Right? Note that there is also in the correction network there is also this nice residual connection, which sort of ensures that certain characters which don't need any processing can use this short circuit path. Right? So overall, the soft masked BERT gives really good results in terms of correcting out any kind of characters that might have been incorrectly typed by the user, uh, and thus helps in better spell correction in an offline manner. Now, these spell corrected suggestions can be fed into the try, can be indexed into the try, and then can be used for the most popular completion baseline for autocomplete systems. Okay, so all of that is good. And it's nice that we have systems in place so as to handle defects in an offline manner and as well as handle defects in terms of full queries. However, sometimes when users are typing in prefixes, they can make errors there as well, errors there as well, right? Um, and then what you need is online spell correction. Right? For example, consider a user who is trying to type WhatsApp, but for whatever reason ends up typing WATS. Now, it might be a good idea to take this and apply some sort of a conversion rule. Let's say if you have a conversion rule somewhere which says that you can convert WAT to WHAT, then what you would do is to convert WATS to WHATS and then search into the try. Okay? So this kind of online spell correction needs to be there to improve the coverage of spell correction mechanism, right? So offline spell correction can do only certain level of things. It can work on full queries, but it can't work on incomplete prefixes, right? Uh, so thus, a mechanism which works on incomplete prefixes, short prefixes, is much more powerful and can guarantee more coverage in terms of improving and avoiding spell correction errors. Uh, Spell mistakes happen when users are typing for a variety of reasons, like users are typing too quickly, very quickly, and therefore end up typing some characters double two times, right? It can also happen because of keyboard adjacency and the fat finger problem. So sometimes you end up, like you end up typing as TEH. So that is also another popular mistake, right? Inconsistent rules. So sometimes you may type you may type you may come up with mistakes because English is deceptive in nature. Sometimes you have IE, sometimes you have EI, and so on. Right? Uh, Ambiguous word breaks. So people can type silver light or silver light together. New words, right? New words basically tend to have lots of spelling mistakes. Of course, there are spelling mistakes because of non-standard words, for example, especially in languages which are phonetic oriented. Okay? So in such cases, the broad idea of the method is as follows. Typically, there is a try which is indexing all of your queries, right? All of your historical queries, like so and it also indexes the score with respect to each of those queries. The queries which score the highest are given preference and they are shown to the user. Okay. Um, Now, while leveraging this try, if there is a spell correction, then clearly the subtree or the subtry that you get to is going to be very sparse or very poor. The scores are going to be really bad, and you do not really want to show results. For example, for WhatsApp, WATS may not lead to very good results. Right? And therefore, the idea is let's assume that you have some sort of a conversion table, which tells you that a subword like WAT can become WHAT. Similarly, if the user has, for example, typed in FACPO, you may use a conversion rule which converts CPO to CEBOO and make it like CEBOO Facebook, right? And that can surely lead to way better suggestions in the subtry compared to FACBAW, which may lead to nothing in the subtry, right? In the subtry. Yeah. So the idea is that if you have a conversion table, right? And we'll talk about how to get that conversion table. But if you have a conversion table, you could essentially jump from one node into the try, which is not so promising, to a more promising node into the try, right? While incurring the conversion cost. So these conversion rules, of course, they have to be learned, but then they also come up with conversion costs, right? So the idea is that even after you incur that conversion cost, you must get to a part of the try which is really, really rich in terms of awesome suggestions. And then you apply the conversion rule, else you don't apply the conversion rule because applying conversion rules doesn't come for free. Okay. So that's that. Now, the idea is as follows. Typically, if you were trying to essentially extend the query, if the user has typed in A, right, and you want to sort of, uh, the user has already typed in A, and then you want to sort of convert it in the sense that maybe A is the wrong prefix the user has typed in. Maybe the user was meaning to type B, right? So, and let's say that there's a conversion table that you already have. So each node is basically going to store a score, which basically in the try, which says that how good that particular candidate is in terms of showing it as a query to the user, right? And then you also have a conversion table, as you see here. Now, when you apply the conversion rules, you incur a cost. So if you were to predict A itself that the user has typed, there is no conversion cost because, hey, the user typed A. So therefore, the score of the suggestion A is 3000. But then if you convert from A to B, right, the score is going to be 1000, but you also incur a penalty of 5000. Okay, incur a penalty of 5000. Okay. So remember, in this particular try that is being shown, the higher the score, the worse the suggestion. Okay, so in some ways, the scores are in the opposite directions. You could think the lowest score is the best one. So therefore, you could basically add the scores, try scores, and penalty nicely here. Okay. So similarly, if you were to think of replacing A with D, well, the table says that you incur a cost of 6000 as well as you have a score of 1000. So that's basically the overall score. Or basically, if you want to, convert the prefix A to C, well, you incur a cost of 5000 plus 5000 because, well, this is 5000 and you incur a cost of 5000. Okay. And then you can sort of sort it by the scores and then return the lowest one because remember we said that lower the score, the better the overall quality of the suggestion is. Yeah. Now, the idea is that this has to be implemented in a A-star search kind of a way because it has to be done in limited latency. So you try a conversion rule, check if it leads you to better results or not. Try another conversion rule. Your table is going to have insanely large number of conversion rules. So you're going to actually check these conversion rules against the try and sort of try to expand using an A-star search on top of the try so as to do all of this within the latency budgets. Now, the big question is, how do you get these conversion rules, right? So it turns out that in this paper, it is sort of explained nicely how you could basically leverage past query logs along with a noisy channel, Markov noisy channel based method so as to learn these conversion rules. The idea is pretty simple. You basically take these pairs of queries which have spell corrections being shown by the search engine, right? So basically, there are queries where the original query was something, and then there is another query, right? And you want to essentially learn from these small conversions whether if you want to correct a particular word to another word, what is the kind of rule that makes sense? Okay. Um, a particular model called as the Markov engram transformation model is sort of learned by looking at a lot of these conversions in the past. You first take your original query and the transformed query, break them down into smaller subsequences. In this paper, they call them as transfemes, right? And you can decide what is the maximum size of the transfeme that you prefer. So you could prefer transfemes of size 3, or you could prefer transfemes of size 1 or 2, and so on. And then use those popular conversions so as to learn probabilities associated with each of those transfeme conversions. That leads to conversion rule table, right? So essentially, you learn a large conversion rule table, and then, hey, you're going to use this conversion rule table along with the try using the A-star search algorithm. Okay. So that's basically a method to actually do online spell corrections for prefixes as the user are typing in those things. And even if they're making errors while typing stuff, you still show suggestions which are going to be related to the corrected prefix and the suggestions coming up by matching the corrected prefix against the try. There's yet another model which has been proposed more recently, like in 2018, which also tries to do the same thing. However, this time using deep learning method, right? So if you see in the previous method, no deep learning has been used. This Markov engram transformation model was learned using a noisy channel method, which is not deep learning oriented at all. And you were just using the typical tries. So now this new method that we're going to talk about is based on character RNNs. The character RNNs here, the goal is to first take the user prefix and then do two things. First, correct the user prefix if required, and second, come up with completions. Okay, so correct the user prefix and come up with completions. All of this must be done in real time. That's the idea. Okay. The interesting part is that while you're correcting, you have to ensure that the edit distance between the corrected part and the actual part is not very large, right? You must not correct to something which is completely very different, right? So you have to make sure that your edit distance is not very large, right? And second thing that you have to ensure is to maximize the probability of using the language model. So the typical encoder decoder probability generation probability that people care for. Now the interesting part is that if you have, let's say, m characters in the user type prefix, and let's say that the prefix was completely correct, there was no error at all, right? You would just use the RNN encoder decoder model so as to come up with more characters in the prefix and try to maximize the probability of generating the next few characters, right? And typically this is done using the beam search algorithm. This is a traditional beam search algorithm where the user has typed m characters so far. You essentially check for every possible character that can come next and then as candidate, and then try to maximize the probability, find the most probable candidates and continue to keep the best probable candidate. So, if the beam width is k, you'd want to continue and maintain the k best solution so far. At the next time point, you are going to, add one more character to it and continue until you get an end of sequence symbol, in which case you dump that candidate as the final result. That's a general beam search without any error correction. Now consider the another case where your input is m characters and your output needs to be n characters, where you basically can have an error in the prefix, right? So if there's an error in the prefix, as we discussed, you want to incur a penalty for every edit that you do, right? You don't want to do too many edits because otherwise you may end up changing the entire prefix, right? But you don't want to do that. So therefore, you have to add a penalty for every substitution you do or every deletion that you do. Of course, you don't want to add any penalty for the new characters that you're generating, right? Because, if the user typed WATS, well, if you insert a new character, there is a penalty, right? There's a penalty for this character. But after that, whatever characters you generate, there is no penalty for these, right? So therefore, the edit distance formula has to be appropriately modified so as to have no penalty for the extra characters that are added, but incur a penalty for every substitution, deletion, or insertion that you make otherwise in the original user type prefix. The problem is the following. The problem is the latency problem. Now, for every character that you are generating from the character RNN, you have to make sure that your edit distance is not very large. So you have to calculate the edit distance for every character that you generate, right? With respect to the input prefix, right? And then you have to also make sure that your beam search algorithm is basically generating k-best candidates every time. So at every point of time, if you were doing things in the traditional manner, the dynamic programming algorithm for edit distance is going to cost a lot. It's going to cost m into t time, where t is the remaining string that you generate, right? And m is the already length of the existing prefix, right? So it's going to take a lot of time, right? However, and in fact, if you basically integrate it with the beam search, the edit distance part with the beam search, right? It would basically take that kind of time, right? Where C is the size of the character set. So let's say if you're English, right? I mean, like maybe 50 characters captures all of English, right? Including small letters, capital letters, and punctuation marks and so on. So that's C, right? R is the number of candidates that we keep, the beam width. M is the size of the prefix, and N is the size of the final completion. So it's going to take insanely large amount of time, specifically because of this N square. So you can't incur that much of time. But there's a very cute observation. The observation is that edit distance computation is based on dynamic search algorithm, which basically computes the edit distance one character at a time, right? So that's that. If you have looked at the dynamic search algorithm for edit distance, you know that you basically compute the edit distance for a larger string based on the edit distance of a slightly smaller string. And same thing goes for beam search. It also grows one character at a time. Now the two processes can actually be merged together. The two processes can be merged together, and your original beam search algorithm, which never bothered about edit distance, can actually be converted into another algorithm which cares about edit distance uh, by a very small change. The idea is that the original algorithm only cared about the generation probability of the next few tokens given the prefix tokens, given the prefix characters, right? Now you need to care about edit distance. So see here, this part is the prefix part. This part is the new thing that is being generated, new characters being generated, right? The string that is being generated. So you care about the edit distance and the generation probability of the generated output, right? So the language model probability. So the broad idea is that what you have done is to amortize the computation, the dynamic programming computation required by the beam search and by the edit distance, and put it all together so as to do this stuff, so as to do the error correction in the prefix as well as high probability language model based generation together, right? Integrated the two processes together and therefore get it all done within limited latency budget. Okay. So that was, error correction, online spell correction using character arrays. In short, in this video, we talked about how to handle defects um, in query auto-completion systems. We looked at LSTMs for inappropriate query suggestion detection. However, more recently, several transformer-based methods have also been proposed, specifically for, well, they have not been proposed, but people have been trying them uh, specifically for multilingual scenarios, right? So now there are transformer-based methods and very, very awesome multilingual encoders like XLM, XLMR, InfoXLM, filter, and so on, which people have used so as to predict whether a particular query suggestion is inappropriate or not. Uh, we also talked about offline spell correction using, the soft masked BERT method. But well, there are also other methods for offline spell correction. And lastly, we talked about online spell correction, where we were looking to spell correct the prefixes that users are typing in. We looked at both a deep learning based method and a non-deep learning based method. More recently, there have been some efforts towards trying to do generation in a toxic sensitive manner. So essentially, all these transform-based methods like GPT-2 and so on, they are not sensitive to generation of toxic content. However, there are methods which are recently proposed like DXperts, which essentially learn a separate language model for toxic generation and separate language model for non-toxic generation at runtime, sort of combine the outputs from both of those methods so as to lead to non-toxic generation from transformer-based methods. Right? So that's a direction which requires more work. So currently, the experts method requires you to build three different models and store them in RAM, which may not be the best thing to do for query auto-completion systems. And therefore, this kind of area needs more work clearly. Right? Okay, so that's it for this video. Thanks a lot for watching. Hope you liked it. Connect with me on LinkedIn or have a look at my research on my homepage. Thank you.